we've been talking about the ball and spring model of solids, in which we zoom down inside a solid, and we realize that what's inside is a regular array of atoms, regular three-dimensional array of atoms bonded together with chemical bonds. And we've been modeling the massive nuclei surrounded by the inner electrons as massive balls, and the covalent interatomic bonds as springs, because in fact they behave very much like macroscopic springs. So that's a useful qualitative model. We've done some quantitative things with it. We've actually figured out from stretching wires and knowing the density of the material, an actual spring stiffness for interatomic bonds in different materials. But we ought to be able to make other actual quantitative predictions, numerical predictions about things that happen with solids based on this model. So one of the things that's interesting to think about is this is one of those tracks that we've been putting carts on, but for our purposes today, it's just a long bar of aluminum, about 2.3 meters long. Let's think about what might happen at the microscopic level if I took this piece of metal and I just whack the end of this bar. So I just tap it like that. Well, thinking about the ball and spring model of a solid, what I've done is I've applied an impulse, a brief impulse, to the atoms at the end of the bar, right? So in fact, they're going to gain some momentum in the direction of the impulse, and what that's going to do is it's going to, among other things, it's going to compress these interatomic springs. So now a very short time after I've applied the impulse, these atoms at the end are moving in the plus x direction, and they're also compressing these first bonds. Well, we didn't apply an impulse to these atoms, but now that these spring-like bonds are compressed, these atoms actually start to feel a force too, because these compressed springs are pushing on them. So in a very short time, this atom starts to feel a force that way due to the spring on the left. I'm going to call it force left. And so a few nanoseconds later, this atom's going to start moving to the right. So now we better redraw this down here. So now what we're going to find, and I'll just draw one chain here, is that because this compressed spring exerted a force on this atom, now after a few nanoseconds, this spring is compressed. And what's happened here? Well, this spring also exerted a force backward on that atom, so at some point it may, depending on what's going on, it may actually be that this spring might even be stretched now. And so now we have a force that way on that atom. This spring is now pushing back on that atom. This spring is maybe now even stretched, so it's pulling back on that atom, and this spring is now pulling. So we start to have a lot of forces on all the atoms that have been affected. And now, of course, because there's an impulse being delivered to this atom, it's going to gain momentum this way, and it's going to disturb this atom. And so what we're going to get is a disturbance that propagates all the way down. Bonds get compressed, and this it's really a wave. It's what it's called. This compression wave moves all the way down the big chain of atoms in the bar. Now notice that the atoms at the end don't move down, so no mass moves. It's just this disturbance, this compression of the bonds that moves down, and any given atom probably is displaced only a very small amount from its equilibrium position. So what moves down is not atoms, but a wave, a disturbance, just like a wave in a stadium. If you all raise your hands and the next people raise their hands. Can we do that? Yes. Can we do a wave? Can we start a wave over here and then have it go over there? Okay, 1, 2, 3, go. Perfect. Perfect. And notice that no students moved from one side of the room to the other, but this wave, the disturbance, moved. So no matter moved, but some energy moved, disturbance moved. So that's what should be happening in here. The atoms are very close together, and there are a lot of them, but they're doing the wave. And so we actually ought to be able to detect the fact that this disturbance gets all the way down here. The speed at which it travels is called the speed of sound in a metal, in the solid, in this case aluminum. And what does it have to do with sound? Well, what sound is, when you hear sound, it's a disturbance in the air that propagates toward your ears. So if I clap my hands, it takes, through the air, sound travels at about 330 meters a second, so it takes a short time before people in the back row can hear it. What's really happening? We're getting, I've compressed some air and then it expands, and this compression and expansion is a pulse just like the one we described, except the air molecules aren't bonded to each other, so we're just getting pressure fluctuations. They move out until they hit your eardrum, and then a pressure fluctuation can make your eardrum vibrate, and that's what you hear as sound. So it's kind of a similar thing. In a solid, we get these compression fluctuations that go down. So in principle, we actually ought to be able to measure the speed of sound in a solid like aluminum, and that's what we're going to try to do here. So what is this setup? Well, we have a bar, and we have this metal rod that I'm just going to bang on it with. And down here at the other end, not quite touching it, we actually just have a microphone. And so the idea is, if I bang on this end and we get these compression of bonds moving all the way down here, it eventually gets here, and it compresses some air, and that disturbs the microphone. And so if we could time how long that took, then we'd actually be able to measure the speed of this sound wave, sound pulse going through the aluminum rod. So that's what we're doing. We're using a computer interface like the ones you've used in lab. So it's exactly the same Science Workshop interface. The microphone's plugged in here, so we're looking at, and the green curve here, which is a little hard to see until we get here, that's the signal that the interface is getting from the microphone. So basically, absolutely, it's a little noisy, but basically nothing is happening until it starts to get something right there. And this is a plot versus time. And so as it says down here, one of these squares is 1/10 of a millisecond. So we can just read times off the graph. The red curve is a signal due to that's started by an electrical contact that's made because this metal rod is actually connected to a 9-volt battery, which is also connected to the bars, the tracks, so that when I make contact between this metal and that metal, it completes a circuit, and we just get a little electrical signal, and that starts the timer going. So, and it's a little tricky to do this. It's not super precise, but we ought to be able to get a fairly, if we're lucky, we'll get a good indication, so we may have to do it a few times. Okay, that's not bad. So when the red trace starts, its contact was made, it starts counting. When this goes up is when it reaches the microphone. We'll do it a couple more times just to make sure we get a sort of something that keeps looking roughly the same. Okay, well, one more time. That's actually a better. That didn't do anything. Oh, come on. Oh. All right. Well, it seems to be looking like that, so we'll use that data. Okay, so we ought to be able to figure out the speed at which the pulse traveled just by figuring out how long it took and knowing the length of the bar. Okay, so the bar is a little bit longer than 2 meters. It's 2 meters, it's pretty close to 2.3 meters, 228 centimeters. So we have 2.3 meters was the length, the distance the pulse traveled, and we have 1, 2, 3, 4, 5.2 maybe squares till we get a significant signal for the microphone. So we're not being super precise here. So we have 5.2 times 10 to the negative 4 seconds, because each square is a tenth of a millisecond. And if we work that out, that should give us the speed of sound in aluminum. So let's work it out. So 2.3 divided by something like 4,400 meters per second. And so fast, right? So you may have wondered how we know that the signal reaching the microphone is really going through the bar and not through the air. The answer is, of course, it does travel through the air, but the speed of sound in air is about 330 meters per second, so it takes a lot longer for the sound to get to the microphone through the air. So the first thing we detect is indeed the sound going through the bar. Yes? Well, okay, so how long should it take for it to get there? So the question is, shouldn't we see another spike when the sound gets to the microphone through the air? But let's see how long that would take. It would be 2.3 meters divided by 330 meters per second. So what does that come out to? About 1/100 of a second or something. So about 7. So it should take about 7 times 10 to the negative 3rd seconds, which is 70 times 10 to the negative 4th seconds, and so it's off our graph. Okay, we don't have enough time on that. We didn't look at it. We're not plotting enough time on the graph for us to see it. So yes, in principle we should. So okay, so we can measure the speed that sound propagates in a particular solid, and not surprisingly, it's different in different metals, because density, but what does density have to do with our model of sound propagation? Can we say it in terms of the density is different, but how does it translate to differences in our microscopic model? Okay, so the length of a bond, that distance, that's going to be different. What else is different in a different metal? The spring stiffness. Some metals are really soft and some are really stiff, right? Gold is much softer than aluminum, so this interatomic spring stiffness is different. What else is different? Let's go back to density. It's not just radius, it's what else? Atomic mass. Atomic mass. So the masses of the atoms are different. So the parameters of our model here are different, so it's not surprising that we're going to get different values for the speed of sound.